In this video, we have this force field and we want to find the flux where S is the part of the paraboloid, z equals 4 minus x squared minus y squared, that lies above the square, x is between 0 and 1, and y is between 0 and 1, with upward orientation. Okay, so now we're going into all these vector fields and finding the flux of these particular surfaces. So let's start off by graphing this guy. So notice that we don't want all of the paraboloid, we only want a part of it. So graphing this guy kind of gives us, well, the paraboloid in this case is oriented in the z direction, which is nice. It's going up 4 units. Now we don't want all of it, okay, because you can see that I want only a portion of the paraboloid. Okay, so let me go ahead and just write it like this. We only want the paraboloid, oops, let me go ahead and write it a little bit better. We only want the paraboloid that is between, and kind of in the first octant, where x is between 0 and 1, and y is also between 0 and 1. So if you kind of attempt to draw, you can imagine that the paraboloid is broken up into the octant, and all we really want is this part of the paraboloid. So if you imagine this paraboloid being like this, we only want the square that's associated with that part. So the point that is associated with this point that's associated with that point, and the point that's associated with that point. So we only want part of the paraboloid. We don't want kind of the whole thing. We only want that part. Okay? So we want to find the flux. So obviously there's a vector field that's being acted on here. This is a vector field. And there's some flux, there's some thing going on. Water. This might be like a part of your umbrella. You want to know in the upward orientation. Okay, so we want to make sure that all of our vectors are pointing upward. So in order to find the flux, well, let's first start parametrizing this particular surface. And my surface is a paraboloid. So this is a very easy parametrization. It's a basic one. Notice that the paraboloid is not closed, so we can't use the divergence theorem. So my parametrization is just going to be x equals x, y equals y, and then z equals 4 minus x squared minus y squared. You can see that my z is going to be g of x comma y. All right. So if you wanted to write x comma y, my parametric equation, that's just going to be x comma y comma 4 minus x squared minus y squared. That's going to be my parametric equation. Okay, so to find the flux of a basic parametrization, so flux is of the double integral over the region S of the force. To find the flux, we got to take the force vector, multiply it by the normal vector over the region ds. And luckily, whenever we have a basic parametrization like this, all we really got to do is take the double integral over the region d, take negative p times partial g over partial x minus q partial g over partial y plus r dA. And remember that this is with positive orientation. You can only use this formula if your parametrization is nice, just like this one. It's not like a sphere or a cylinder, because then we got to go back to the cross product. And then you have this guy. This would be the formula. So now all we really got to do is plug everything in there. So we're going to take the double integral. Negative p, that's going to be the first component of my f vector. It's going to be xy. Okay. And then and it's going to be negative. That's going to be that guy. Multiplied by the partial derivative of g. Now remember, g was this guy. So the partial derivative with respect to g, the partial derivative of g with respect to x will just be negative 2x. Minus q. So q in this case would be the middle one, yz. Now we have to be careful because there's no z's in here. Okay, so z doesn't exist. So z in this case is actually going to be this guy, y minus x squared minus y squared. So the z, this z right here, is just the 4 minus x squared minus y squared. Okay, so that's that guy. That's my q. And now we got to multiply it by the derivative of this guy, but with respect to y, which in this case will be negative 2y, okay? Plus my r. And my r in this case is going to be this zx. Remember, there's no z's in here. Z is taking into consideration this guy. So z is going to be this 4 minus x squared minus y squared again. And then you have an x on the outside, and then there's nothing being multiplied afterwards. So dA. So we're plugging everything in there. Remember, there's two integrals, so you should only have two variables. In this case, x and y are going to be the two variables that I choose. And then if I see a z, what I'm going to do is I'm going to plug in whatever z was for my parametric equation. So let me multiply a couple of these guys out, because this is going to be a really terrible thing. So the double integral over the region D of positive 2x squared y. Then this guy is going to give me a positive, okay, so this is going to give me, I'm just going to write down what I ended up getting. So plus 8y squared minus 2x squared y squared minus 2y to the fourth plus 4x minus x cubed minus xy squared. Okay, so this is what you end up getting when you FOIL all of that out, dA. Okay, so you get a huge mess. So let me just make sure that I write it down. You can confirm with me to make sure that you actually got this when you FOIL everything out by pausing the video and then double checking. All right, and now we need to figure out the limits of integration. Now this would be really terrible if we had to convert to polar. So I hope we don't have to do that, because converting to polar would mean that I'm gonna have a whole bunch of squares. Now luckily for us, our region is nice. It's just from 0 to 1 and 0 to 1. So it's so nice. So it's gonna be from 0 to 1 and 0 to 1. So 2x squared y plus 8y squared minus 2x cubed, x squared y squared minus 2y to the fourth plus 4x minus x cubed minus xy squared. And then here we can just write dx dy. So we're going to take the derivative first. I'm sorry, the antiderivative with respect to y, with respect to x. Oh gosh, I'm tired. Okay, so with respect to x is going to give me 2/3 x cubed y plus 8x y squared minus 2/3 x cubed y squared minus 2xy to the fourth plus 2x squared minus x to the 4 over 4 minus x squared over 2y squared from 0 to 1. Okay, so that's what you should kind of get at that point. When you take the antiderivative with respect to x. All right, and now what I'm going to do is I'm going to plug in the ones in there. So the first one's going to give me 2/3 y plus 8y squared minus 2/3 y squared minus 2y to the fourth plus 2 minus a fourth minus 1/2 y squared. The zeros all just go away, so I'm just going to have just dy. So now what I can do, I can just group a couple of things over. So I'm going to have this negative 2y to the fourth by itself. Then when I group the y squareds, I'm going to get a positive 41 over 6y squared. And then 2/3 y plus 7 over 4. So I got that from the constants. And now finally, all we got to do is just take the antiderivative of this guy. So we get negative 2/5 y to the 5 plus 41 y cubed over 18 plus 1/3 y squared plus 7/4 y. So here's the antiderivative of that. And when you plug in the ones and put it in your calculator, you're going to get 713 over 180. So this would be the flux going through this paraboloid in the upward orientation.